Yeah, we are doing some basic review about functions, right? That's what we started last time. We talked about domain and range. These are things that I think everybody already knows about. One thing I want to get to about functions is sometimes we talk about functions in pieces, or these are called piecewise functions. Piecewise functions, these are those functions with like the big curly thing that is not so hard to deal with, but sometimes a little confusing. Things that look like this, f of x equals, and then this kind of thing, right? X squared if x less than 1. This is just a made up example here. 5x if x is greater or equal to 1. That's an ugly looking greater or equal. All right, this is a piecewise function because it's really sort of one function which has two separate formulas, and you use each one depending on what the x value is. All right, and so for example, in this example, if I had something like, what is f of 0? F of 0, as always, means you plug in x equals 0 to the function, but when it's in pieces like this, you have to decide which is the appropriate one to plug it into, and you look at these guys, right? If the x is less than 1, in this case I'm trying to do 0, the x is indeed less than 1, and so I should use the first formula, and I get 0 squared, which of course is 0, right? If I did something like f of 4, again you look over here to see which piece I'm going to use. F of 4 is the x, 4 is bigger than or equal to 1, so I use the second piece, and I plug 4 in right here. So this becomes 5 times 4, which is 20, right? And so on. What about f of 1? 1 is kind of right in the middle there, but oops. Nothing special. You know, you still look over here and you test which category does 1 fall into. It's the second, because 1 is greater than or equal to 1, right? So I use the second formula. I get 5 times 1, which is 5. All right, this is a simple piecewise function. All right. You can also draw the graph of a function like this. I mean, sometimes you can, at least if the two pieces are things that you already know how to draw the graph of. It's not so hard to draw the graph. So what I'm going to do to graph it, I'm basically just going to graph both of the two pieces, and then the true graph has sort of one for part of it and then the other one for another part of it. So to graph the two pieces, now in this case, it's easy enough to graph those two pieces. The first one is y equal x squared, which I hope everybody knows looks like a parabola that goes up like this. So I'm going to graph that one first. Maybe I'm going to do this sort of in another color. This is not my final answer, right? But anyway, this is the x squared part. Can you see that all right? Yeah. And then I'm going to graph the other part also. It is 5 times x. Can anyone say what that looks like? The graph of 5x? Yes, it's a straight line with a slope of 5 that goes through the origin. So that slope of 5 is fairly steep, I guess. Something like that, right? It's probably actually even steeper than that. But all right, that's the 5x. Okay. Now, this is not my final answer. Because that bunch of stuff there isn't even a function. I have two y values for all the x's. How do we make this into that piecewise function? Well, you just take the parabola part for all x values that are less than 1, and you take the straight line part for all the x values which are 1 or greater. So my true answer is more like, I'll draw it in red here, and then I'm going to redraw this because it's a little messy, but I take the parabola part for all the values that are less than 1, if this is 1 right here, and then I take the straight line part for all the values that are equal or greater than 1. So it's like that. So my true final answer looks like this parabola until you get to 1, at which point it just sort of stops and then changes into this line, like so. All right? This is the graph of the piecewise function. Sometimes I'll put the little arrows on the end of my lines to indicate that they go on forever. Sometimes I don't do that. It's just the kind of guy I am. All right? So this is how you would graph a piecewise function. I would say just graph all the pieces together first, and then decide for yourself where each piece needs to go. All right? Any questions about that? This is not terribly difficult. All right? Excellent. Some very important functions actually come in pieces, and there's one particular example that we are going to look at fairly often, and that is the absolute value function. Actually, the absolute value function, its definition is in terms of pieces. If you want to write a formula for how you find the absolute value, everybody knows the absolute value is you take a number, and if it's already positive, you just leave it like it is, and if it's negative, you make it positive, all right? The graph, anybody know what the graph of the absolute value function is? You can show me with your hands. Yes, I see this kind of thing. This kind of thing, it's the V shape with a sharp point at the bottom. So the absolute value function, its graph, looks like this. Now, for most purposes, you don't really need to write a definition of the absolute value function because, like what I just said, everybody knows it's just like you make the number positive, and if it's already positive, you just keep it positive. But those words that I just said are not terribly useful if you want to actually compute things with formulas involving the absolute value function. So this actually, we can write it as a formula using pieces, right? We can write it in pieces because it does seem to me, when I look at this picture, you can think of it as sort of two separate things which are just joined together, right? And to me, it looks like I've got this piece over here. This is the first piece, is the line on the left, which is a line of slope -1. And then there's also the piece on the right, which is the line of slope +1, all right? So I'm going to this is actually the true definition of the absolute value, is as this thing in two pieces. I'm going to go to the next page here. It worked. So I'll just draw this again, just so everybody knows. But the two pieces, I'm going to say, I'll say this is the real definition of the absolute value, is that the absolute value of x it's in two pieces. Now I'm going to write, some stuff here, and if x, whatever. Anyone want to suggest where should the two pieces sort of shift from one to the other? That's what this business is. I have two pieces. It does one thing for one part and another thing for another part. What do you say? 0. Yeah, 0 is the point at which it switches from being one to the other. So I'm going to say it does something if x is less than 0, and something else if x is greater than or equal to 0. Now, in this example, it doesn't really matter which one you said is or equal, right? You could have said less than or equal to 0 and greater than 0. Let's try and fill in those two blanks over there. What are the formulas that you use for each piece? Let's talk about the piece on the right first. This is a straight line with slope 1. Anyone tell me the equation for such a thing? X. Yeah, this is like one of the simplest equations ever, right? X. All right, that's the part on the right side is a line with slope 1. The part on the left side is a line with slope -1, so what's that going to be? You just shout it out. -x, I think, is what they said. Yeah, this is it. This is the true definition of the absolute value. Next time your little brother asks you, hey, what does the absolute value mean? You can say this, and they won't understand what you're talking about. I say, don't you just make it positive? Yeah, that's what you do. But this is the technical definition of what the absolute value is. It's a little strange. I mean, your little brother will probably say, wait a minute, aren't you supposed to make it positive? Why is the answer negative here? What would you say to your little brother? Yeah, because this case is happening when x is already negative. So this is actually not negative. The x itself is negative, and you put another minus sign and it makes it positive, all right? This is confusing to your little brother, but we sophisticated college students can understand this, all right? This is the true definition of the absolute value sign. Any thoughts about that or questions? If you ever need a formula for the absolute value, this is it. It doesn't, unfortunately, there isn't an easier formula than that. Not a big deal, though. All right, excellent. So that was my very brief kind of discussion of piecewise functions. They are important in the real world. They typically happen when you have when you're trying to talk about something which, for some reason, just changes all of a sudden, which sometimes happens in the real world. All right? This is all I wanted to say about section 1 in the book. Chapter 1, section 1 is about just sort of a general overview of functions. Functions can be given with an equation or with a graph or with just a description in words of how you get the answer or with a bunch of data points. All right, these are functions. Everybody knows about functions. What about, so the next section in the book is section 1.2. Section 2 is just kind of an overview of what they call essential functions. Essential functions. This is another section which will be basically all review for all of us, but I want us all to get on the same page about what kinds of functions I expect you to be familiar with. And I hope that you actually are familiar with all of these. So I'll write a little list here and then we'll talk in more detail about these. So there's the linear functions, there's polynomials. These should sound familiar. There's ordinary, just like powers of x, which are related to polynomials. Here's some words. I don't know if you are familiar with this terminology. Not a big deal. Rational functions. There are certain functions which are called rational functions, and then there are functions which are called algebraic functions. Even if you've never seen those words, I bet that you do know what those things are. They've probably just not been described in that way. And then we have the trigonometric functions. That is like sine and cosine and such. The exponential functions. Exponential means the x appears inside the exponent, like e to the x or 2 to the power x is an exponential function. And then there's also logarithmic functions. All right. Actually, these exponentials and logarithmics we are not going to talk much about them at all in this class. They are mostly covered in Calc 2. So I'm just going to say in Calc 2. We are going to talk in detail about the rest of them, though. Which, by the way, sorry, I meant to say this at the beginning. Some people ask me about textbooks. So the textbook for this semester is the same as the one that we use in Calc 2. I checked. It is also the same as the one that we use in Calc 3. I've never taught the Calc 3 here. So if you are a math major, or otherwise if you know that you're going to take 1, 2, and 3, then you might as well get the book for the long haul. It might be cheaper to just straight up buy it at that point rather than renting it for 3 semesters, although I don't know. Also, somebody else asked me if Calc 2 is required for the finance major, and it is not. I looked that up too. I don't know if anybody else cares about any of that, but any questions about anything I just said? All right, excellent. So let's try and just go down the list here. Linear functions, polynomials, powers, rational functions, algebraic functions, and the trigonometric functions. Probably we don't need to spend much time reviewing these, although the trig functions, in my experience, are a good thing to go over. All right, let's do it. I'm going to go to the next page. So let's talk about linear functions first of all. That is lines, right? The standard form of a line is this, and you absolutely need to know how to work with the equation of a line in this form. This is called the slope and intercept form. And I hope you remember this. This is sort of the easiest or the simplest way. Usually when you want to consider a line, this is the way that you want to write it in most contexts. All right. The m here is a number, which is the slope. And the b here is the y-intercept. That is the location of the y value when the line crosses the y-axis. All right? This is the slope and intercept form of a line. So if I show you a specific example of a line in this form, you can easily graph it because you will know what the slope and the intercept is. So for example, y equals, let's say 3x minus 6. How would I graph it? Well, the minus 6 is the y-intercept, so that's down here. Negative 6, say. Maybe I'll actually draw all the little guys. And then, so the line goes through that point, and then it has slope of 3. And remember the slope you want to think of as the rise over the run. So the 3 I think of as 3 over 1. That means it goes up 3 and over 1 to the right. So this line, when I draw it, I'm going to start here. I go up 3 and over 1. So right there is another point on the line, right there. And if I again were to go up 3 and over 1, it would actually end up right on the x-axis. And then this is what the line looks like. Right? Everybody knows, everybody loves the slope-intercept form of a line. Any questions about that? I hope this sounds very familiar to you. Great. I was recently talking to my 8th grade daughter about the slope-intercept form of a line. So we've been doing this for a while, I think. Okay, sometimes this you definitely need to know. I mean, you should have this form of a line memorized. Sometimes you need to use what we call the point-slope form. This one is less commonly used, and I would say you probably don't have to have this formula memorized, although it's not. I mean, it's not a big deal to memorize it, but here's the point-slope form. There's a few different ways that people like to write this, but I'm going to write it this way. So this is another way to describe a line. This is used when you want to write the formula for a line, but you don't actually know what the intercept is. If instead you know what the slope is and you know one of the points that it goes through, then you can use this formula to write the line. So this m is, again, the slope. And those other things, x naught and y naught, is a point on the line. So if you don't know what the intercept is, but you do know it goes through this or that point, and you know what the slope is, you can use the point-slope form to figure out what the equation of the line is. So for example, if I'll draw a picture and ask you to find the equation of the line. Let's say like this. Let's say it goes through that point, and then it also goes through this point, maybe. This is the line, all right? I kind of missed the points there. Just make it thicker. That's my pro tip. If you miss the point, just thicken it out a little. All right. What's the equation of this line? Well, you can choose. Actually, I'm going to use one of those points, and you could use either one. Let's use this one. This point here is 1, 2. That's going to be my chosen point that I'm going to use in the point-slope form. And then I also need to know what the slope is, which you can tell by looking at my fabulous picture here. The rise over the run, you think from one of those points to the other, how far up do you go, how far over do you go? I think it goes up by 1 and over by 3, right? If my picture is correct. So in this case, the m is 1 over 3, right? Up 1 and over 3, that's the slope. And then this special point, the x naught, the y naught, is that point 1, 2. You could have also used the other point if you wanted to. You'd get the same answer eventually, although the intermediate steps might not look the same. All right. Anyway, what's the equation of this line then? So the line is y. I'm using this, plug into that formula up there. Y minus 2 equals 1/3 x minus 1. All right. This is the equation of a line. Typically, if someone asks you the equation of a line, they want you to write it as the slope and intercept form. So to convert this into the slope and intercept form, I would just distribute on the right side and then add the 2 over there. So you would be, sorry, I got to turn the page. It was y minus 2 equals 1/3 x minus 1, right? So if I distribute the 1/3, it's going to be y minus 2 equals 1/3 x minus 1/3. Add the 2 to the other side. Y equals 1/3 x minus 1/3 plus 2. And if you want to combine the fractions there, 2 is 6/3 minus 1/3 would be 5/3. All right. So this is the formula for the line in the slope and intercept form. So apparently the y-intercept of this thing is 5/3. All right. I believe it. Any thoughts about that? This is pretty much all I'm going to say about linear functions. Not a whole lot to say about it. All right, I hope you are all masters of the straight lines. All right, great. Let's talk about, the next thing on my list was polynomials. This is also something that I hope that you are all very familiar with. Polynomials. All right, these are things that look like, here's an example. Maybe I'll use f of x. F of x equals something like 8x to the 5 plus 7x cubed minus 2x squared plus x minus 7. I'm just making this up, all right? This is a polynomial. What it looks like is a bunch of powers of x added together with coefficients in front of them. And in order to be a polynomial, technically the powers here must be positive integers. Integer meaning whole number. All right, you're not allowed to have like a 1/2 power. That is a thing, but it's not a polynomial. All right, polynomials have integer exponents. Okay, every polynomial has a degree. I hope you're familiar with that term. The degree is just the value of the highest exponent. So this one that I wrote there, this one has degree 5. And the degree is super important, when you're talking about polynomials. A lot of things depend on the degrees. And there are special names for polynomials of various degrees. A degree 1 is always going to be a line. A degree 2 is a quadratic. Degree 3 is cubic. Those are pretty much the ones that we care most about in this class, at least. All right. It's going to come up all the time. You are going to need to be quite comfortable with factoring a quadratic. So I just wanted to do a couple quick examples of that. Factoring a quadratic. Everybody needs to know how to factor quadratic polynomials. So let's just do a bunch of examples. Factoring, what that means is something like this. I give you a quadratic, and your job is to write it as a product of two linears. And there are, everybody learns how to do this in high school or whenever you learn how to do it. People learn how to do this in different ways, and I really don't care how you want to do it as long as you can do it and get the right answer. This one, I would say, they tend to be easier if there's no coefficient in front of everything here. So there's no number here. That means that these are going to be x and x here. You probably learned some tricks about if they're both positives here, everything is added together. It means they're going to be pluses here and here. X plus something and another x plus something, right? Sometimes there would be x minus somethings in there, but in the case when all the original signs are pluses, they're all going to be pluses. And then the strategy, you just have to basically guess what these two numbers are. And it's not much of a guess. It has to be two numbers where their product is 12 and their sum is 7. That's because of the way in which you would expand this by doing the FOIL. The way you get this last number is by multiplying these two together. And the way you get the number in the middle is by multiplying this and then adding it and multiplying it with this. And so these two numbers, they have to multiply to be 12 and they have to add up to be 7. Is that possible? What do you say?
Yes, it is.
Yes. What should I use?
4 and 3.
Yeah, 3 and 4, or 4 and 3, however you want. So 4 and 3. All right, x plus 4 and x plus 3. This is how you factor that one. Okay, let's just do a couple quick more. How about x squared minus 8x plus 7? All right. Now, when you see a minus in the middle and a plus on the end, what that means is that the two factors each have minuses. That's because the products of those two numbers have to be positive 7. So when I multiply these together, it's going to be positive, but when I add them together, it's going to be negative. The only way that can happen is if these two numbers are both negatives. Anybody think you know what should the factors be here? Shout them out. Yeah. Yeah, x minus 8 and x minus, 7, not 8. Thanks. They have to multiply to 7 and add up to 8. Great. X minus 7 and x minus 1. All right, I hope everybody is hip to this. Here's another one. How about x squared minus x minus 2? This one, now when you see two minus signs in there, that means that, well, really it's, if this term here has a minus in front of it, it means that these two numbers, one will be positive and one will be negative. So you have to think of two numbers. One's going to be positive, one's going to be negative. When I multiply them, I get negative 2, and when I add them up, I get negative 1. What do you think? Yeah.
Negative 2 and 1.
Yeah, minus 2 and plus 1. X minus 2, x plus 1. You can put them in whatever order you like. All right. My strategy for doing these is basically you try to guess the answer, and usually it works out. And if your guess doesn't work, then try harder, I guess. All right. I don't have a clear memory of learning how to do this. When I was in like 8th grade, maybe, is when I learned about factoring. I don't think my teacher taught me a method, really. It was just like, yeah, you just got to figure it out. All right, let's do a harder one. Harder when there's a coefficient in front of the x squared. So that would be something like, how about this? Can we factor that one? All right. This is harder. Again, I don't really have much of a method other than trying to guess the answer, but there's some basic principles that you can use here. You know, it's going to be the fact that there's a number in front of the x squared here, it means that these x's inside the factorization, they themselves will have coefficients in front of them. So what I'm looking for is basically something times x and then another something. And here again, I'll have something times x and then another something, all right? The rules about the signs in an example like this work the same way. So because they're both minuses on the inside, I know that these two signs, one will be a positive and one will be a negative, which is not very helpful to me at this point. And I know that these two numbers in front of the x's, so here and here, they have to multiply up to be 3. Because when you do the FOIL to expand this thing, the front term there, the 3, will come from multiplying this times this. So whatever those two numbers are, they have to multiply together to be 3. Anyone want to guess two numbers whose product is 3? 3 and 1. Yeah, that's the only way to do it if it's going to end up being whole numbers. So let's just start off by, I might as well just say, they're going to be 3 and 1, right? Oops. Didn't mean to do that. They're going to be 3 and 1, okay? 3 and 1 here. It's just a matter of filling in the other two numbers, and this is where I'm going to have to do some more intense guessing, I suppose. The other two numbers, their product has to be 4, and there are several ways in which you could do that. So I'm going to, here's the way that I write this out. As I said, however you want to do this is totally fine with me. It could be a 2 and a 2, right? That's one way that you could get 4 by two numbers which multiply to be 4. Or it could be a 1 and a 4, or it could be a 4 and a 1 in those positions, right? You have to separately check these two options because it might be that the 1 goes next to the 3, but it might be that the 4 goes next to the 3, and those would be different answers. So you do have to consider those two orderings. And now, which one is it? And in this case, I'm just going to try and sort of check each one of these and see which of them does actually add up to 11 in the middle, all right? And what I'm looking at is when I multiply the 2 on the inside, that makes 2, and then the 2 on the outside here makes 6. So could you somehow add up 2 and 6, or maybe subtract them and have them add up to 11? The answer is no, you can't. So that means this is not the correct answer. Because those ones, when I do those products, they do not add up or subtract up to be 11. What about the 1 and the 4? So what you want to do is multiply here and here, right? Because we are doing like, in the steps of the FOIL, we're looking at like the outers and the inners, right? On the outside, we have 3 times 4, which is 12. On the inside, I have 1 times 1, which is 1. Can I make the 12 and the 1 add up to 11? The answer is yes, I can. If you make one of them negative, which is what we have to do here. So I want to make, in order to get negative 11 in the middle, I want the 12 to be negative and the 1 to be positive. And so that means it has to be minus 4 over here, because the 4 is the one which makes the 12, and then plus 1 over here. And this is the true answer. 3x plus 1, x minus 4. All right, this is how you factor that. This is the way that I do it, at least. If you have some other method to use, that's totally fine. And hopefully it takes you less than 10 minutes. It took me a long time because I was trying to explain every little thing. But this one, hopefully you could do in less than a minute, certainly. Any questions about that? This is harder factoring. All right, great. This business about factoring is useful principally because it allows you to solve for x in a quadratic. This is mostly why we want to factor things, although it's also useful in canceling things in a complicated formula. Sometimes you want to factor so that you can cancel. But generally speaking, we can solve for x by factoring. I just want to do a simple example like that. Something like solve for x in a quadratic equation, something like this. 2x squared plus 4 equals negative 9x. Can you solve for x? You do this by factoring. The first thing you should do is put everything on one side so that it equals 0, because I want it to look like just a big sort of standard looking quadratic polynomial. So to put everything on one side so that it equals 0, I'm going to add that negative 9x, add it onto the other side. You must set it equal to 0 before you try to factor it or anything. And now let's factor. So it's going to be like this, all right? The two coefficients on x have to multiply up to be 2. So it's going to be, I'll put 2x and then a 1x as the other one. And then for the other number, I have to choose two numbers which add up to 4, so that when we multiply them across, two numbers which their product is 4, so that when we multiply across and add them all up, we get 9. So just like last time, it could be a 2 and a 2, or it could be a 1 and a 4. It could be a 4 and a 1, right? Does anybody see how this can work out? If you choose those two numbers, you want to make it so that the inner plus the outers adds up to 9. Yeah?
2x plus 1 and x plus 4.
All right, let's see if I agree. So in this case, if you do it in this way, when I multiply, the inner product is just a 1x, and the outer product is an 8x. And when I add them up, I get 9x. So I think this is correct. I hope you all agree. Any thoughts about that? It is a little tricky if you're out of practice, especially. All right, these are the factors. Anyway, I was trying to solve for x, right? This is still equal to 0, right? It used to be in the previous line that quadratic thing was equal to 0. You factor on the left side, it's still equal to 0. And now, since I have two things being multiplied together, right here, those two factors, their product is 0. That means either the one thing is 0 or the other thing is 0. So you split it up now. You say 2x plus 1 is 0, or x plus 4 is 0. And we're going to get two separate answers here. You solve each of those for x. The first one I solve and I get x is negative a half. The second one I solve and I get x equals negative 4. These are my solutions for x. So this is how you solve for x in a quadratic equation. Set the whole thing equal to 0, factor it, split it up into two simple, linears, and then solve each of those. Any questions about that? All right, this we're going to be doing quite often. So if this is a little shaky to you, you might want to refresh your memory a little bit. All right? Great. One other way to solve a quadratic is the quadratic formula. And we're going to use it maybe every so often, probably not very often, but you will from time to time want to use the quadratic formula. So I will just refresh your memory. This is another way to solve a quadratic equation without doing any factoring at all. You don't really have to think much to do this. You just plug everything into this nasty formula. It's not so nasty. The quadratic formula. So it says if my polynomial looks like this, ax squared plus bx plus c equals 0, then the solutions are, it just tells you straight up what the solutions are for x. I hope you remember the quadratic formula. It's minus b plus or minus square root b squared minus 4ac. Everybody knows all over 2a. Everybody loves that part. All over 2a. Yeah. That's the quadratic formula. So this will give you two answers because of the plus minus in there. When you take the plus, you get one answer. When you take the minus, you get another answer. I mean, usually you get two answers. Sometimes you, by some kind of coincidence, you only get one answer. And sometimes you get no answers if the thing inside the square root is negative. But that's the quadratic formula. All right? Any thoughts about that? So I will expect you to know the quadratic formula. I hope that you do. Okay? Great. Uh-oh. TikTok notifications. This is my kid's iPad, which I'm using temporarily. So I had to turn off her texting notifications because as soon as like the school bell rings, she's getting tons, like 10 texts per minute, mostly from Juliana. You know what I'm saying? Juliana. Yep. Juliana the Queen is what it says in her text. Yeah. Yep. This is the 6th grader, actually. I have a 6th grader and 8th grader. Yeah. Juliana the Queen is a 6th grader. All right. Yeah, we just let her have TikTok, even though she's not officially old enough. Like the TikTok rules, you have to be 13. She's 12, but I don't know if that was a good move or not. She appreciated it, but we'll see. Ask her in 20 years if it was good for her or bad for her. One last thing to say about polynomials. Sorry. Yeah, we got 10 more minutes. Graphs of polynomials. Generally speaking, it's difficult to draw the graph of a polynomial. If I just showed you a polynomial of high degree, it is not really a simple method to draw the graph. Of course, if it's degree 1, that's a line, which you can do. If it's degree 2, that's a parabola. And I think most people learn how to graph a parabola in high school or something. That you have to just know a few little tricks. But for our purposes, we're not going to care so much about that, although it is a good idea to know just vaguely what the graphs of a polynomial generally look like. So graphs of polynomials, I'm going to try and describe this in somewhat vague terms, but graphs of polynomials look like curves, curves with some number of, I will say, turns. I'm being informal here, but I'll show you what I mean by drawing some pictures. And in fact, the number of turns is predictable. It's always the degree minus 1. So the number of turns is the degree minus 1. Here's what I mean by that. A line, a linear, is degree 1. It has no turns. It just goes in a straight line. There's no turning back and forth in a line. But a quadratic, which is degree 2, it has 1 turn. And we all know, a quadratic, when you graph it, it looks something like this. This is a degree 2. It looks like a curve with 1 turn. What I mean by turn is basically like this point here, is where it turns around. All right. A degree 3 is a curve with 2 turns, which looks generally something like this. All right. Just like a quadratic doesn't always have 2 answers. Sometimes it could have fewer turns by some weird coincidence, but generally speaking, a degree 3 will look like this. All right. Not always, but that's the usual case. A degree 4 looks something like this. It has 3 separate, so the turns would be like those 2 points over here, and on a degree 4 has 3 turns. All right, etc. So this is generally what polynomials look like. And the 2 ends of the polynomial, if you look sort of far to the right or far to the left, they always either go all the way sort of down to infinity or up to positive infinity. And depending on if the degree is even or odd, either they both go down or they both go up, or one goes up and one goes down. All right. Okay, this is what polynomials generally look like. Actually, here's a little preview. We will be talking later on in this course about There is actually a general method by which you can draw the graph of any polynomial. It will take you a while, but even that polynomial that I showed you, like at the very beginning, the degree 7 one, you could draw the graph of that using some fancy calculus ideas. Well, that one, I don't know if the numbers will work out when you want to factor things, but there is a method using calculus to graph any polynomial that you want. All right, this is all I want to say about polynomials. Okay, I hope this isn't too boring. I mean, these are things that I just want to get everyone on the same page with. We got a few more minutes. We can talk about powers. That's the next type of function. Powers of x. Here I'm just referring to like individual powers, you know, a function that looks like f of x equals a to the n. If n is a whole number here, then that is a polynomial. In fact, that's a polynomial with only one term. And there's a word for that. Anyone remember the word for a polynomial which has only one term in it? This is an obscure word which is not important that you remember or not. You remember? Nah, it just has one, like, you know, y equals 8x to the 5. This is a polynomial, but it only has one term. That's called a monomial. Remember that word? Monomial, yeah.
I was thinking something with mono, but then I was like, it might be wrong.
Yeah. Monomial. I'm probably not ever going to say that again. This is not an important word for our purposes. But little fun fact. Tell your friends at dinner. They won't be your friends anymore. All right? Okay, yeah. Functions of this type. So, like I said, if the n is a whole number, then that's just a polynomial. But if the n is something else, it can be something more interesting than that. And there are some sort of special cases for when the n is some other weird numbers. This can be an interesting type of function. So, for example, special examples here would be if the n is -1, then I'm talking about f of x equals a to the n. Sorry, I meant to say x to the n. I don't know what I was talking about. X to the n. I hope that's what you interpreted that as meaning. Just a power of x, right? If that power is -1, we have x to the -1. This is also known as, what's another way to write that? Yeah, this is also known as 1 over x. This is a more common way of writing that. So if you allow that exponent to be something other than a positive whole number, you can get functions which are really quite different. This 1 over x is very different from any polynomial. The graph of it looks something like this, right? It has a vertical asymptote at the origin, right? This is 1 over x, another important function, right? And it is just a power of x. More generally, everybody knows, I hope, if you ever have a negative number in the exponent, this is the same as 1 over x to the n, right? And this will be a common thing. Actually, in this class, the former version is usually more useful than the second one. So, like, it will happen often that you see something like this, and it gets better when you rewrite it this way as a negative exponent. We're going to do that all the time. Using the negative exponent is often more convenient for the purposes of what we're going to do in this class. Another special exponent is the 1/2 exponent. This would be when n is a half. X to the 1/2. This is the square root of x, right? Another very important type of function, which is very different from a polynomial. The square root of x, the graph looks like this. It doesn't exist at all to the left of the origin, because there's no such thing as the square root of a negative number, at least not in real numbers. All right. And then more generally, if you have some other weird fraction, it gives you some other kind of root. So if the exponent there was a 1/3, that's the cube root. Everybody knows that, right? That's the cube root. If you have some other fraction that maybe doesn't have a 1 in the numerator, if you have something like, 4/7, this you would rewrite as the 7th root of x to the 4. All right, so this is how you would interpret a weird fractional exponent that's not 1 over 2 or something. And this turns out to be the same if you calculated it as this number. You could also do it this way around. So the 7th root of x to the 4 is the same as doing the 7th root of x and then taking the 4th power. All right? So these are just powers of x, but they are very important other types of functions which are very different from the polynomials. Anything to say about that? We got 2 minutes. That's enough time for me to tell you what a rational function is. There's a YouTube. She rings that bell too much. Rational functions, let me just tell you. Rational functions. This is a fancy word for another type of functions, a rational function. Anybody know what this means? Maybe this is a word that everybody knows. I don't know. It involves a fraction. That's a hint. That's why it's called rational, because it has a ratio in it. No, I'll tell you, since we only got a minute left. A rational function is any ratio of polynomials. That's called a rational function. So for example, a rational function, I'm going to turn the page here, any ratio of polynomials. So something like x cubed minus 2x squared plus x minus 3 divided by x squared minus 4. This is a rational function. It means it's a fraction where the top and the bottom are polynomials. All right? And the graph of a rational function, I'm just going to say very vaguely, they looks like a curve with asymptotes, with vertical asymptotes. It has the asymptotes because in a rational function, sometimes the denominator can be 0. Like in this particular example, the denominator could be 0 if x was 2, or also if x was minus 2. And so this graph, when you look at the graph, it has asymptotes at 2 and minus 2. I actually graphed this ahead of time. It looks, in case you care, it looks like this. It has 2 vertical asymptotes, and then in between, it kind of does like that. And then on either side, it does something like this. This is weird, but it goes like that. All right. So a rational function generally looks vaguely like a bunch of polynomial type curves, but they have asymptotes in between them. All right. That's what a rational function generally looks like. All right. I almost made it through the list. The next was algebraic and then trigonometric. So we'll talk about them next time. All right. See you all on Friday at 2 o'clock. There will be no quiz.